Hi guys, this is the second part of the section 4 of chapter 9, and we are going to learn about how to find oblique asymptote, or sometimes called slant asymptote, and also point discontinuity, which is also called a removable discontinuity, and a hole. And this might also run a little longer because we have to review like long division and synthetic division and things like that. And so if it does run long, then I will cut and then I'll continue the lesson tomorrow. And our plan is that we go over this section today, and then tomorrow we will have a work day for this section because I know there are a lot of elements that you need to know. And on Thursday, we'll review, and I'll open up an online quiz throughout the weekend, but you don't have to complete the quiz until Sunday. So Sunday is your quiz day, but based on your preference, like if you just review so it's fresh in your mind, so you want to take the quiz on Thursday or during the weekend, you can do that. Oh, actually, Sunday is a Palm Sunday. So the quiz isn't actually due till Monday night, okay? So, and Tuesday will start 9.5. So I wanted to give you some flexibility because this weekend is supposedly a 3-day weekend, and I do want you to rest because online school can be very exhausting because you're just working, and you're always at home. So, so that's the plan. And so you have a quiz on Monday, but I'll open it up on Thursday night, so you can access it anytime through Thursday night to all the way Monday night, okay? So yeah, I want to give you some flexibility in that sense. All right, so we are going to start with a problem from your homework from last section, which was number 5. And I didn't want you to graph this, but I wanted you to find out vertical, horizontal asymptotes based on how we learned it, and then x-intercepts and y-intercepts. So let's start with the vertical asymptote. Vertical asymptote was found by setting the denominator equal to 0. So x plus 2 is equal to 0. So then x is equal to -2, and that is my vertical asymptote. Horizontal asymptote was a little different because you have to remember the 3 scenarios. So the degree of the numerator is 2, and then degree of the denominator is 1. So then the numerator has a greater degree. That means we don't have a horizontal asymptote. 0 was by setting the numerator equal to 0. So let me try that. X squared plus 8x plus 20 equal to 0. So usually when you see a trinomial with the power of 2, you will try to factor. But this one, you might see that factoring might not come as easily. So then you have to remember the quadratic formula. So the quadratic formula goes -b plus minus b squared minus 4ac over 2a. So a in this case is 1 because it's 1x squared, b is 8, and c is 20. So -8 plus minus 64 minus 4 times 1 times 20. Okay, at this point, I'm actually going to stop because you can see inside the square root, it's a 64 minus 80, meaning that it's a negative answer. So there is no real 0. So this one will give you imaginary 0. So I will just say real 0 does not exist. Okay, so there is no real 0. What that means is that your graph does not touch the x-axis. It's going to just be either above the x-axis or below the x-axis, okay? Let's talk about the y-intercept. Y-intercept is found by plugging 0 into x's. So it's 0 squared plus 8 times 0 is 0 plus 20 over 0 plus 2. So it's 20 over 2, meaning 10. So my y-intercept is 0, 10. So that's how you have done this number 5. So that's a review, and let's look at today's lesson. So today's lesson involves oblique asymptote. So oblique asymptote has a very special condition. Basically, to have an oblique asymptote, your degree in the numerator has to be bigger, but not just big. It has to be 1 bigger than the degree of a denominator. So basically, if you can add 1 to the degree of a denominator, and if it equals the numerator degree, then you have an oblique asymptote, and no horizontal asymptote because your numerator degree is greater. But to find the oblique asymptote, you actually have to divide the numerator by the denominator. So if you can remember from the polynomial chapter, there are 2 kinds of division. You could either use long division or you could use synthetic division. And I'm going to show you both because I know some of you will prefer one over other. So let me try with the long division first. So long division setup goes like this. X squared plus 8x plus 20 goes inside of this upside L and upside down L, and then x plus 2 goes outside. And your goal was to think, okay, what can I multiply to x to make it x squared? Because that's the first one that you want to get rid of, and it's x. And once you found that x, you have to distribute that x to the divider. So x times x is x squared, x times 2 is 2x. And then you always subtract. So this goes away because x squared minus x squared is 0, and that's my point. Like, I want to get rid of the first one. And then 8x minus 2x is 6x. And then this one comes down, plus 20. And then I think, okay, what can I multiply to x to make it 6x? Because I want to get rid of 6x. And it's plus 6, right? 6 times x is 6x. 6 times 2 is 20. 12. And then again, we subtract. And then it becomes 0 and becomes 8. But the remainder doesn't matter. Actually, what I want to know is this, x plus 6. And y equal x plus 6 becomes my slant asymptote. I know this is very interesting, right? Oblique asymptote or slant asymptote, they're the same. So what does it look like in a synthetic division? It looks like this. So synthetic division setup was getting all the coefficients from the numerator. So it's 1, 8, and 20. And then you always have to think about, okay, what x value makes x plus 2 equal 0? It's negative 2. Right? And then you bring down the first one always. So 1 times negative 2 is negative 2 and 6. And you stop here because I don't really need to know about the remainder. And so you only need the first two. So then how do I write this? Well, this used to be x squared, but then we divide it by x. So this becomes x. So x plus 6 is my slant asymptote. Okay. I hope that makes sense. So again, you need to remember that the oblique asymptote doesn't exist in any numerator. It only exists when the numerator degree is 1 greater than the denominator degree. So let's determine if it has an oblique asymptote, and if it does, then let's try to find. So degree of a numerator in the first one is 3, and then the degree of a denominator is 1. So 3 is greater than 1, but it's not 1 greater than 1, right? So there is no oblique asymptote, and I'm going to just skip to the next question. All right, number 2, degree of the numerator is 2, and then degree of denominator is 1. So the numerator has 1 greater degree than the denominator. So this one does have an oblique asymptote. So we have to find out what the oblique asymptote would be. And I'm going to use the synthetic division because I find that easier. Well, x equals 0, right? Because you need to make it 0. So 6 comes out. 6 times 0 is 0. And so then it's just negative 3. So what that means is that your oblique asymptote is actually 6x minus 3. Because I don't really care about because the third column will give you a remainder, but remainder doesn't matter in the slant asymptote or oblique asymptote. So that's why I'm doing it this way. I know this might be a little bit confusing in the beginning, but you just have to remember that I don't care about remainder, but I do have to divide. And so I just stop before I get the remainder. Okay? I mean, you can continue to the end, just disregard the last column. All right, last one. So this one you might be thinking, well, like how do I do this? Well, there are two approaches. You can FOIL the top part, the numerator, and then get the x cubed, or you can just be a little bit more clever and try to actually factor the bottom and see what happens. So the top is just this, but then if I factor the bottom, it's x minus 4 and x minus 2, right? Because two numbers that multiplies to 8, but adds to negative 6. Then if you look at it here, they cancel out, right? So then my, this is what my rational function looks like. So then the degree of the numerator is 1 greater than the degree of a denominator. So we divide. But this one you have to be a little bit careful because when you do the synthetic division setup, you do 1 because 1 is a coefficient of x squared, but there is no x, right? That means the x coefficient is 0, and then you have negative 4 as a constant. And then x minus 2 has to equal 0, so x is 2. So then you bring down the first one, and then you multiply 1 times 2, and then you add. So, and then I stop because I don't care about the remainder. So then my oblique asymptote is x plus 2. I'm a little bit nervous about you guys understanding this concept, but I hope that makes sense. Okay, let's look at the whole. And then we'll practice a lot more tomorrow, okay? So please watch this video if necessary, but try the homework, and if it's too hard, please email me so that I can go over the homework problem. Point discontinuity is very interesting because you actually have to start by factoring everything. So it's a very good habit to factor everything once you found what you needed to find. So I said that when you cancel out something, then that becomes a point discontinuity. And what I mean by that is this. So this one, if I factor out the top, it becomes x plus 5 and x minus 1 because 5 times negative 1 becomes negative 5. 5 plus negative 1 becomes 4. So then you will see that how the top cancels out with the bottom factor, right? So this just looks like x minus 1. And if you graph this, it will look like x minus 1 graph, which is like this. If this is my x and y axis, it has a y-intercept of negative 1, and it will look like this, okay? But remember, if you just consider the very first form of the rational function, x plus 5 equals 0, x equal negative 5 should have been my vertical asymptote. But that got canceled. So what that means is that where it used to be 1, 2, 3, 4, 5, vertical asymptote, which is here. Sorry, you can't really see it because it's now what it does is that when it passes the negative 5, it has a hole. That value doesn't exist, okay? Because your original function had a limitation in the domain, which was x couldn't be negative 5. So even if you cancel out, that still stays true. Okay, I know this is a very strange concept, and that's why we always start with the domain restriction. X cannot be negative 5. But then when we simplified everything, well, my function now looks like x minus 1, but it still holds true for your domain that cannot be negative 5. So you will see your graph having an empty place in your function, okay? I only have 30 seconds, so I'm going to go over these examples in the next lesson. If you could understand the oblique asymptote and how to find it, then that's great. And try to apply what we learned about point discontinuity just a little bit. So basically, if you cancel, whatever got canceled is your point discontinuity. But I will do more practice tomorrow. And so, yeah, good luck.